nothing but just the extension of the Fourier series. Remember again, this for those who maybe need a quick reminder. For periodic signals, we have Fourier series, and we have a fundamental, basically field, which in this case is T naught, and based on that, we have a fundamental frequency. Question?
So the signal has to be finite, QT, to do this?
For the Fourier series or Fourier transform?
Or the signal has to be finite?
No.
No.
For example, the e power of -8 cell, that's not finite, right? Whatever. And you can take Fourier transform. Okay, so for this one, this is a periodic signal. We have fundamental period, and then we have fundamental frequency. F dot 1 over T. Okay. And if I want to write the Fourier series, what frequency do you think I will have in the Fourier series? What frequencies will appear in the Fourier series of this one?
That's all. And reduce it as
Huh?
And reduce it as well.
Multiples of F naught. Yeah, good. So I will have F naught, I will have 2 F naught, I will have 3 F naught. We call it harmonics, right? And also the negative ones. So basically, if you plot Dn, and you have a DC component. You have D0 as your DC component, you have D1, you have D2, D3, and then correspondingly D negative 1, D negative 2. And you remember, what's the relation between Dn and D minus n? They are conjugate symmetry, right? So it's Dn and D minus D negative n, for example, D3 and D minus 3. What's the relationship between them? Are they equal? Yeah, they're conjugate symmetry, meaning that the magnitude is equal, the magnitudes are equal, and the phase are opposite. Okay. So this is for periodic signal. Now, if I just look at one period of that and consider a periodic signal instead of Fourier series, we are going to have Fourier transform for that. Fourier transform. Now, for the Fourier transform, see, this is the critical difference. Instead of having discrete frequency, F naught, 2 F naught, 3 F naught, we are going to have all the frequencies available. Okay, so this is what it makes the difference. So here we are working with continuous, and we call it GF. GF is continuous here. Where it says here Dn, n is discrete, right? N could be 0, 1, 2, 3, etc. Here n could be anything. All the frequencies could be available, and everything is else the same. We have magnitude of GF, we have phase of GF, we have this magnitude or conjugate symmetry condition that, let's say, G of F and G of negative F. They are equal in the magnitude, and the phase is opposite. So then everything is the same. So if this is the magnitude of GF, you see a symmetry here and an odd symmetry here. Let's say it's like that. The phase could be like that. Okay. Even odd. And I guess hopefully you got also the interpretation why this is the case. Basically, if I increase T, the period of this signal, if I increase it, it's like it's always replica. You're gonna go to plus infinity, always go to negative infinity, and I'm gonna get that. So therefore, in the limit that T naught going to infinity, basically this will generate that one. T naught going to infinity means that F naught going to 0. F naught going to 0 means that now I'm working with all these little frequencies that starting like really a small one. So as if I will have all the frequencies. So this is the question.
So it has T naught goes to infinity. Doesn't the amplitude go to 0? Because it's 1 over T naught? I don't understand that.
What's 1 over T naught?
The amplitude, the end.
In the formula, you mean?
Yeah.
Yeah, so the formula, it changed. Right, let's look at the formula. Yeah, so let's put them back to back. So this is what I like. When you put them back to back, you get a lot of things. So this side is the Fourier series,
Oh, okay.
and then the other side is Fourier transform. So let's see what's going on. So here in the Fourier series, I can write gt, this is the exponential term, as summation of dn, some exponential multiples of f naught. Here, instead of summation, you have integral. I'll tell you the other time. Always when you go from discrete to continuous, sigma is converted to integral. Okay? And gf is exactly the same as dn. Like the role that gf and dn play are the same. Dn, Fourier series coefficient, Fourier transform. They are like equal. Okay. Now look at here. E to the power of j 2 pi ft. So basically you have all the frequencies. Versus here you have e to the power of j 2 pi the same nf naught. Okay. So basically all the multiples of f naught. Here you have all the f's. So all the same. And this is called the signal synthesis, meaning that you somehow I don't know, write your signal in terms of its details or its components. And this is signal analysis, which is nothing but the Fourier transform. So the Fourier transform is just, anybody can tell me the interpretation of this integral? You have gt and then you have this exponential. What's the interpretation of that?
Is that correlation of the two?
Good, yeah, exactly. So you have basically you have gt, and these are your bases signals. Bases functions or signals. So I have infinite of them. E to the power of j 2 pi ft, and any f that you can think of, you know, f1, f2, whatever. I mean, for all the f's. So you have infinite of them, and you have all the f's. Now what you do, you just correlate or project gt over all of this. And that's going to give you, for example, if this is, let's say, if this frequency is e to the power j 2 pi, pick a frequency, 1 hertz, t, then the corresponding projection on that basis would be g at frequency 1. In the graph, if I find f equal to 1, that's going to be that amount. And then if somebody says, let's say, pick this point, 2.3 hertz, whatever, 2.4 gigahertz, something that way. Okay, so the question is that how much 2.4 gigahertz my signal has? I don't know. Let's correlate it. I find the corresponding basis, e to the power of j 2 pi, f is 2.4 giga times t, correlate it, and then I know how much of that frequency I have. Okay. So the physical interpretation of Fourier transform is to look at your signal in the time. By looking at this, I don't know what frequencies do I have. Okay. But when I take the Fourier transform, then I look at this, and a lot of things I can say here. For example, oh, okay, I have this frequency, maybe I don't have any high frequency, maybe I have a DC. So a lot of things can come from the Fourier transform. So it's very practical. One of you asked me, is this practical or not? It's very practical, okay? Again, because when you look at the signal in the time when I'm talking, okay, and somebody asks you, okay, what frequency in this speech, you have no idea. But when you convert it to the frequency domain, when you check the Fourier transform, then you can see a lot of things. Okay. So hopefully as you go through the course, you're gonna get more practical insight on this very important subject. Okay, and hopefully I expect everybody just remember this formula, like very simple. GT is given by this integral, GF is given, with this integral. The only difference is that here you have plus, here you have a minus sign. Okay. And this is also very interesting. The relationship now between what's the relationship between Dn and Gf? Anyone can tell me what's the relationship between Dn and Gf?
And 1 over the period.
So so basically these Dn's, now let me just multiply also by T naught, are the samples of Gf. Okay. So basically if I had an aperiodic signal and I had this purple line, let's say as my continuous GF, this is for the aperiodic signal. Now if I make it periodic, then the Fourier series are just the samples of that. Okay. So this is GF evaluated at multiples of F naught, and this is the F. Okay. So we're going to see one example. That the Dn is the samples of GF. And we saw this example. Very nice example to show that we have a signal, time domain signal, it's for minus ATUT, and then in the frequency domain, this is the GF. This is the magnitude, this is the phase. You see the magnitude is even, the phase is off. Did anybody get a chance to plot this in MATLAB? No. Yeah, if you have the time, just plot it and then vary different values of A to see by changing A. But changing A means that you're changing the rate of drop of the signal in the time domain. Okay? And see what happens to the basically in the Fourier domain, what happens. I guess intuitively, if your signal drops faster, okay, if it drops faster, it will have higher frequencies, okay? If it has higher frequencies, means that here, higher frequency component will be larger. So, as we go here, these are like high frequency components, and around here, let's say they are low. So if I have a signal that doesn't vary too much, I would expect it to have a lot of low frequencies. If I have a signal, let's say like this, okay, so it doesn't change a lot. Okay, something like that. Then I would expect if I take a Fourier transform, I would have a lot of, low frequency components. Everybody agree? Okay, versus if I have a signal. So this is low frequency, or in the time domain, let's say, low variance or something. Doesn't vary too much in the time. Translate to having a lot of low frequency components. And in versus if you have something that changes a lot of high frequency, a lot of variation in the time. If I take the Fourier transform, probably you're gonna see something which has a lot of also high frequency components. You see the difference? So as the frequency goes high, still you have a lot of large components. Makes sense, everybody? You're so quiet. Yeah? Yeah? Okay.
Just watching.
Okay, that's good.
You did a good example last Wednesday.
This one, that's different ways of. Yeah, so these are all just maybe introduction. And now let's do another signal, delta. Again, delta is always a good thing because everything related to delta is very easy. So we're gonna find the Fourier transform of delta. we have to take it. Very simple formula that everyone should remember. Gf is integral of gt equals minus gt pi f. Gt, just put delta here, it's not gt to delta. Okay, now delta t times some function. What's the result of this? Just one? So we have to evaluate these at t equal to 0. Yes. So if I put t equal to 0, this is 1. But don't forget, delta is still there, right? Right. So then we're going to get delta t times each object by epsilon t 0. So anyway, so integral of delta is 1. Right. So therefore, it says that if in the time domain you have a delta in the time domain. If I take the Fourier transform, if we look at the Fourier transform, Gf is 1 for all the frequencies. So in other words, all the frequencies are present in the delta. Remember we had something similar in the periodic version, impulse train, we had the same thing. We're gonna get back to that. But anyway, so impulse, again, because it's 0 and then it goes to infinity, comes back to 0 again, so that makes it to introduce all the frequencies. All frequencies are present in delta t. That's the physical interpretation. For all the frequencies, it's not that you only have low frequency or high frequency. All the frequencies are equally present. All frequencies are equally present in delta.
On your third line in the interval, is it e to the negative j0 because there's only one case of this, so the frequency is 0?
No, because t, you put t equal to 0.
Because that's
Because delta, you are multiplying delta. Look at the argument of your delta. Because delta is time and t, put t equal to 0. Yeah, when you're doing the Fourier transform, the first line, see the variable is t actually. So the variable that you're taking the integral is t. So f works like a constant. You put 1 here and then that's the Fourier transform 1. You put 2 here, whatever. So what you take the integral is the t, the variable is t. Okay, very good. So now we have very simple and nice properties for the Fourier transform. One is linearity. Can anyone tell me what does the linearity mean? Linearity property. So let's say I have G bar, you can do time, a time domain. The Fourier transform is capital G1. And I have another signal G2. The Fourier transform is capital G2. Okay. So linearity means that if I linearly add my signal in the time domain, okay, the same relationship will be applied in the frequency domain. The same linear relationship. In other words, if I multiply these, let's say twice G1 plus 2 times G2, then it's gonna give me twice capital G1 plus 2 times capital G2. Or in other words, if I multiply this by A1, then Fourier transform is going to also multiply by A1. If I multiply this by A2, Fourier transform also will be multiplied by A2. Okay, so this is called the scalar multiplication property. So you, scalability, I guess. Multiply by some constant, the Fourier transform is also multiplied. Now, if I add them in the time, it's going to be also added in the frequency. So that's why I have AG1 plus AG2. Fourier transform is A1 capital G1 plus AG capital is called the derivative. And that's a very, very nice property because, again, just knowing these two, you can know the Fourier transform of a lot of signals by just this property. So just an example. So we saw that if you have each power of minus, let's say t to ut, what's the Fourier transform of this? 1 over, I guess, j 2 pi n plus 2, I guess, right? This one g bar. And then I have delta t, I know the Fourier transform is 1. Now, if somebody tells you, okay, now what's the Fourier transform of 3 times this plus 4 times delta? What's the Fourier transform of that? We know the Fourier transform of this one, we know the Fourier transform of that, just 3 times that plus 4 times that. So what's the Fourier transform? 3 times the capital G bar, 3 times and then 4 times. Okay, so this called the derivative. Okay. Now going back to the relation between dn and ga, remember I said the dn's are the samples of gn. So if you have a periodic signal, a periodic in the time. Then we check the Fourier transform, and the Fourier transform looks like this. Now if you make this periodic or repeat this every t. So now this is periodic, so you're going to have dn. Remember, and then we'll have a discrete frequency, f naught, twice f naught, 3 times, etc. So what it said, what's the relationship between these? It said then you calculate the dn, and then dn is nothing but just 1 over t naught of sample of gn. Okay. So again, if you just scale these, let's say if I scale these by 1 over t naught, then if I sample every, like n equals to 0, you get dc, and then f naught, 2 f naught, 3 f naught, they are going to be equal the same. This is a relation. Fourier series coefficient of the periodic signal repetition is just the samples of this. This is continuous, this was continuous, this was just the samples. Okay, so again, so dn's are, if you just write this in your slide, dn's are samples of 1 over t naught gn at harmonic frequencies of n, meaning that dc, f naught, f naught, etc., and then minus f naught, minus 2 f naught. comparing this in one example. This is the aperiodic signal that I have, something only between 0 and pi, and this is the function e12 minus t over 2 between 0. And this is a periodic version of that. Okay, I'm repeating it every time. It's the periodic version. So for these, I expect to have dn, and we already actually calculated this in chapter 2. If you go back to chapter 2, we calculated dn for this. Now I'm going to calculate gn for this here, and we are going to compare. And we know already there is just a very nice relationship, but let's do that. Okay, this is my GT, e12 minus 80, just between 0. Take a Fourier transform. Very simple formula, the integral GT each part of minus j to pi infinity. Okay, just replace everything. It's not GT, just put here. So why I changed my boundaries from negative infinity to infinity to 0 and pi? Because
That's where you had a value for the function.
very good. My GT only is between 0 and pi, right? See, my GT is 0 here and 0 there. So only between 0 and pi I have that. So that's why I integral change it from 0 to pi. And then each part of something, very simple integral. I take the integral, put the boundaries between 0 and pi. So we get this. Okay, so let's do some simplification. Each power of something 0, right? What do I get here? 0. Yes, I get 1. And then, okay, I get something there. Right, so if you put all of them together, each part of these comes exactly here, and then this term is here, and then you have a common denominator. So after this simple rearrangement, you are going to get this. Please do that at home. Very simple, but it's a practice. Okay, very good. So this is my G. So now what we claim is that, okay, now let's look at GF. So this is a continuous signal, right? Continuous in terms of frequency. If I plot this, let's say, it's like something complex, but for simplicity, let's say this is my GF as a function of F. Okay. Now, I want to show that if I sample this, I'm going to reach to Dn. So therefore, just look at the multiples of F naught. Just look at n F naught, meaning 0 F naught, 2 F naught, etc. So therefore, instead of F, just put upper root n F naught. Instead of F, put n F naught. And F naught happened to be, I guess T was pi, T naught is pi, so F naught is 1. Okay. So you just put here, n times F naught. No, that's fine, because here you have pi and pi, and here instead of f, if you put 1 over, or n over pi, one of the pi cancels, so you get it. That's good. So now this is this, and I guess I have to scale this by 1 over t naught. I just simplify this, you get this. And then I'll compare it with dn from the previous slide. dn was this. G of n f naught. Okay, and then I guess we simplify that. This is nothing but just the dn times t naught. Let's do that. So if this is the n and this is pi, multiply these two together. So dn times t naught gives me again, remember the question is that is this equal to the samples of GF? This is the question. Everybody gets the question? I want to see the relationship. At some point I have dn's, and at one hand I have GF, and I want to see if they are equal. I mean the samples, that they're equal. Okay, very good. So I have this part. Now let's look at the other part. On this part. G of f at that, so I got 1 minus e to the power of minus half pi divided by 1 5 j 2f. So let's multiply these by 2 so that this I get the denominator the same. So then this gives me 1 plus 4 jn. Okay, good. I'm fine with the denominator. Now the numerator, if somebody has a calculator, anybody has a calculator?
We're looking for the,
Yeah, just calculate this.
it's 1.58.
This one, okay. I calculate this.
1.58.
Okay, good. So both of them cannot be divided. Yeah. So there you go. Question?
Was that assuming like n is 1?
No, both of them have n. For all the n's. See, if this one has n, still n is there, still n is there.
Yeah.
Good question. Meaning that for all the n's, 0, 1, 2, 3, and then here correspondingly f naught, 2f naught, 3f naught, etc. They're equal.
My point is, how do you get 1.58 if we're talking about multiple n?
That's talking about the 1.8 is the amplitude,
At 0. Okay, I was asking what value you chose around.
not at 0. This is the height. Okay. So look at this. You get 1.8 divided by this. This one still has the n, right?
Yeah.
Okay. So now what you are saying why this is 1.58?
Yeah, what n did you choose to calculate 1.58?
For all the
Or
n's.
does it count?
All the n's. I never got rid of any n.
1.58 is just the numerator.
What's that?
Oh, you're not saying the entire thing, you're just saying.
No,
0.5
yeah, just the
oh,
numerator,
1.5.
0.5 times, yeah, it's
Okay, I thought you were saying the entire thing was 1.58.
No,
That made more
divided
sense.
by this. No,
Yeah.
divided by this. Yeah.
Okay.
This is the new. The denominator were equal, so I was having it that.
Okay.
I was checking this if they are equal, right?
Right.
Denominator was the same, I was just checking. Yeah, the whole thing has, see, this is the whole thing, has n equal. So for all the n's, they are the same. All the n's is the same. Right. So again, in English term, the Fourier series coefficients, if you want to make it again, write it somewhere. Fourier series coefficients are samples of the Fourier transform. Just it has a 1 over t naught, just in this one. Fourier series coefficient of periodic version of GT are samples of Fourier transform of GT. Yeah.
Isn't it G and FO? Yeah, that's the continuous.
Yeah, that's why I said samples.
So you're going from
Yes,
continuous
you
to discrete.
can say it like this. Yeah, this way. If I sample, I mean exactly that. I have GF, but then I sample.
Thank you.
Okay, very good. So we're gonna get a break in the next few slides. Just introduce some signals, this mathematical notation of some signals, which probably you know already. This is a pulse signal. And this is the notation that we're gonna use, like I don't know what to call it. Maybe gamma, capital gamma. So what it says that if x is between minus half and half, we're gonna get 1. If it is greater than half or less than minus half, we're gonna get 0. And then at point exactly half, you see there's a discontinuity. Let's assume we're gonna get 0.5. That's fine. It doesn't change. Nothing changes. Yeah. Let's say at the point of discontinuity, we're gonna get. Let's try. Okay, so therefore, when you see a gamma t, just have this in your mind. We are talking about the signal, a pulse signal, starting from minus half. And then now, of course, you can manipulate the signal, and I can have gamma of t over tau. Remember, when this is like a, right? If I have the signal and then I have a g of at, everything has to be divided by 8. Remember? So therefore, here, when I say, if I had, let's say, if that's a gamma of x, if I had gamma of 2x, what will it look like? What would be this form? Multiply by 2 and divide by 2. Divide, right? Remember, if you have a, always divide by a. So this will look like 1 over 4. Okay. Now that I have x of my a is 1 over tau. So divide everything by tau. Or by 1 over tau. If I divide this by 1 over tau, I'm going to get this tau. Okay, so therefore you can generate different pulses, different beat by just this definition. Now we can do the same thing for the triangular function. This is the formal definition. So again, if x is greater than half, so when you say absolute value of x is greater than half, it means that either x is itself greater than half, or x is less than half. Anybody?
Negative 1.
Negative 1. Sure. So when we say the absolute value is greater than something, so either itself is greater than that, or it's less than the negative one. And when I say the absolute value is less than half, what does this mean? X is between minus 1/2. So please remember this. When we have absolute value of x is less than a, it means that x is between minus a and then absolute value of x is greater than a. It means that either x is greater than a or x is less than a. So please write down. Okay, good. So So therefore, in this case, if x is greater than half or less than negative half, you get a 0. Now, on this condition, between minus half and half, again you have absolute value here, so let's look at this. If x is positive, what do I get? So usually when you have an absolute value, you have to look at if it's positive or negative. So 1 minus 2 absolute value of x equals, if x is positive, if x is negative. If x is positive, what do I get?
1 minus 2x.
1 minus 2. If x is negative,
1 minus 2x.
the same,
Yeah, it's absolute value, right?
again, the same thing.
1 minus 2x.
1,
Oh, is it? It's switch.
yeah, minus 2, and then this becomes negative x. Remember,
Oh, right, yeah.
if absolute value of x is equal to x, if x is positive, if x is negative, is equal to absolute value of negative 4. 4. Okay. So therefore, when you're working with something negative, this is your whole x, and this is negative. So what you did, I mean, automatically you multiplied by negative in your mind. You did that in your mind. So it's minus x. Right? So when x inside is negative, again, you automatically just multiply it. So therefore, when x is negative, so you get a 1 plus 2x. So if I want to plot it, then if x is positive, this range, 1 minus 2x. So 1 minus 2x is a line. Just put x equal to 0, you get 1. And x equal to 1, because x equal to 1, I get negative. So it's a line like this. It passes 0.5. Yeah. And then if x is negative, the other one. Right. Another line. Okay, good. So and I only wanted to keep it in minus half and half, so I just get it up this far. So I get a triangle. That's how I get two different lines, different slope using this absolute value. Okay. So what you need is just this notation, basically. Understanding what happened here, just understanding the math behind it, and then from now on, when you say delta x, you remember this signal. Okay, this is a triangular signal. Similarly, you can scale it as before, x over tau. Here you have tau over 12 minus tau. Okay, and the next one, no. Yeah, this one is sync function. Very, very useful again function. Sync of x is defined as sine of x over x. I have talked about this several times, but here is the formal definition. The sine of x. How does the sine of x look like? Sine of x. What's the period of the sine of x?
2 pi over t naught. Oh, I'm sorry, it's t naught, yeah.
What's the
Of a regular sine function is 2 pi, right?
2 pi.
Yeah.
So therefore, crossing pi and then going to 2 pi, and this is the value. This is sine of x. Great. if I divide this by x, okay. Okay, so when I divide by x, as I increase x, whatever, for example, if x is 2, I'm dividing this by 2. And then if x is 3, I'm dividing this by 3. So this becomes smaller and smaller, right? That's exactly what happens there. You see the oscillation, and you see exactly it crosses pi and then goes to 2 pi, 3 pi, like similar to a sine function oscillating. The only thing is that because I'm dividing it by x, now it becomes smaller, 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 smaller as I increase x. The same. So points to remember. So for the sync x, exactly the first zero cross, we call it zero crossing. Nora. She promised me to just be quiet and we are breaking. Okay. So let's see, yeah, zero crossing. So the first zero crossing in pi, and then, well, because it's, I mean, the sign of x was periodic and then oscillating, so you will see all pi, 2 pi, 3 pi. And then let's look at the value. What's the value at 0? 1. Why? If you put 0 here, what do you get? Sine of 0 divided by 0. Okay. So therefore, what sine of 0 divided by 0?
It's just 0.
So it is. So I want to evaluate sync function and x equal to 1. So or x equal to 0. So it is sine of 0 divided by 0. What's the sine of 0? 0 divided by 0. Okay. So it's 0 divided by 0, so you have to do some special care or treatment. So what do I do? Pop it up, right? Pop it up. Good. So take a derivative of that. Derivative of its sine is cosine. Derivative of x is 1. And if you put x equal to 0, you get 1. Okay, great. So this therefore happens to be 1. That's why you get 1. You get 1.
About 15 minutes.
I wish she was over duality. I wrote 3/3 of the time shift principle and the duality principle. She fell asleep.
But it's just like, are you
I'm not too sure if she's gonna be over.
that was one, and then
We gotta just have why this is. All the problems are except plus to
made two equations got right equations, but on like the very last subpart, it was like evaluated within this region, and I used that equation, so I got a value. Obviously, if I use the right equation, I did all the hard stuff right. He took like 1 point.
So therefore, please remember this. Okay, so how does the sync function look like? It oscillates, and then its points that are important for me are these crossings and then the height. And let me also give you a trick. Like instead of doing the Hospital rule, we can always say that in this case, sine of x, we can approximate sine of x with x. When x is very, very small. Okay. So therefore, you don't have to really do the. Let's say if I tell you what is sine of 2x, divided by x at 0. What do you say? Instead of taking the derivative of numerator, denominator, etc., just instead of sine of 2x, approximated by 2x. And then x, so this is 2. Have you seen this? Sine of x is no? We can approximate it by x when x is really big.
So really small, like less than 1, you're saying?
Not really. 10 to the power minus 3 minus 1.
Okay.
So here, at this point, we wanted to exactly know what that's at the 0, right?
So it's,
Zero is like epsilon. Okay, very good. So again, these are important. And then let's look at this another example. Sine of 3 omega over 7. Okay, so let's think we want to plot this other than this look like. Again, two things are important: the zero crossing and the height. For zero crossing, it's easy, right? Because this, this is like the sine of this divided by this. And if I have a sinusoid, like looking like that, what's the period of that? In general, if I have sine of some omega naught t, what's the period? 2 pi over omega naught, right? Right? Alright, okay. So I have sine of this. What's the period here? 2 pi over. See now, I guess what confuses you is that now the variable is omega. That's fine. Whatever that variable is, don't worry about that. It could be x, it could be t, whatever. So this is like the, let's call it this a. If you have sine of ax, so the period is 2 pi over a. Okay? So 2 pi over
3 over 7.
3 over 7. Okay, gives me 14 pi over 3. But remember, this is the whole cycle. 14 pi over 3 is the whole cycle. But then, similar to sine, this is 2 pi. But then you have the first zero crossing of pi, half of that. So half of that is your first term. Okay, so let me just give you a general formula then. If you have sine of